In this video, I will talk about our ICLR 2018 workshop track paper, a dataset to evaluate the representations learned by video prediction models. This is a joint project between the University of Michigan and Toyota Research Institute. In the video prediction problem, you're given a sequence of video frames, and what you want to do is predict what the future frames will look like. There's a lot of interest in this problem, in some ways due to its perceived value as an example of self-supervision, since you can train deep video prediction networks without acquiring new labels. Along these lines, prior work has suggested that video prediction networks can help initialize weights or obtain representations that are useful for other tests like action recognition and rotation angle estimation. We want to explore this behavior in more detail by asking two questions. First, do existing models capture important sources of variability in their representations, like object appearance or motion parameters? Second, do trained models generalize to unseen objects and motions, and can we quantify this behavior in some way? These are questions that are hard to answer with existing datasets and evaluation techniques. Up to now, people have evaluated video prediction networks on two kinds of datasets: real video datasets and synthetic datasets. Real video datasets are good for demonstrating generalizability, since objects and motions will differ realistically between training and testing time. However, we don't know the parameters that govern the appearance and dynamics in the video. Then there are synthetic datasets, where people transform objects with predefined appearances in a rendering environment. This lets you evaluate video representations by computing how well you can recover the transformation parameters from them, as long as you log the parameters in advance. However, the sampled objects and transformations don't change between training and testing time, so you don't get to see whether a trained model has generalized the notion of objects or motion. In our work, we combine the benefits of real video and synthetic datasets with the new Moving Symbols dataset. Although it's based on Moving MNIST, a video dataset with digits that translate inside a frame, our dataset includes a lot more features. For example, it supports any number of images per video, alternative image datasets, scaling, rotation, and backgrounds. Also, all the information you need to generate the videos is logged, like the source images and pose information at every time step. More importantly, we make it really easy to change the set of objects and motions that you can sample from. Instead of hard-coding these parameters like existing implementations of Moving MNIST, we define them in a Python dictionary that gets fed to the dataset's constructor. This lets you create a wide variety of video subsets really quickly. To show how useful that flexibility is, we'll use Moving Symbols to evaluate the generalization performance of MCNet, which is a state-of-the-art video prediction network. We'll do this by generating pairs of training and test sets that sample objects and motions differently. For example, we'll have a pair where the training set has slow digits and the test set has fast digits, and vice versa. We'll also generate a training set of slow and fast digits and then test on medium speed digits. Finally, we'll introduce a new icon dataset and evaluate how well the network can predict videos with unseen classes of images. To quantify MCNet's performance, we'll train an oracle network that predicts the class and pose of MNIST digits and report the oracle's performance on generated frames. We found a few interesting things in our speed variation experiments. First, MCNet doesn't propagate the motion observed in the input frames. Instead, it replicates the motion seen during training. For example, if you train on slow-moving digits and test on fast digits, you'll see the digits suddenly slow down in the predicted frames. The opposite will happen in the fast to slow case. You can compare to the in-domain evaluations along the diagonal. MCNet also can't interpolate speeds, which we see when we train on slow and fast digits, but then test on medium speed digits. In the plot, you can see that the predicted location from the oracle network is much worse than in the out-of-domain cases than in the in-domain cases. Another thing we noticed is that MCNet doesn't preserve the right appearance when objects move at new speeds. You can see in the off-diagonal cases that the digits become deformed really quickly. The oracle's classification error also goes up in the out-of-domain case, backing up our visual observations. Moving on to the appearance variation experiments, we found that MCNet overfits to the appearance of objects seen during training, which you can see in the off-diagonal cases where the images transform into digits or icon-like structures. In this paper, we've used our dataset to show the state-of-the-art video prediction model can't generalize to unseen objects and rates of motion. In particular, it doesn't learn the notions of speed or object permanence, which are crucial to predicting future frames in new videos, as well as extracting meaningful representations in a self-supervised setting. Our dataset can objectively measure how well models generalize to new cases, and also how well they internalize physical dynamics. We encourage the community to adopt our dataset in order to develop new models with provable generalization performance. For more information, please check out our project page and our paper. Thanks for watching.